Hey AP Chemisters, this is Mrs. Vanderwall again. I'm trying to finish up the rest of the notes so that we can still have our test on Wednesday. So 12.7 is a model for chemical kinetics. I always found this section to be kind of interesting because it's how these collisions actually occur. And if you think about it, what has to happen in order for a chemical reaction to occur? Bonds have to be broken and new bonds have to be formed. Well, how are those bonds broken? Where do they get the energy to break those bonds? We talked about energy back in chapter 6 and chapter 8, and energy keeps kind of cropping up again. So we know it takes energy to break bonds, but where does that energy come from? Well, molecules must collide. Well, obviously they're moving, aren't they? Must collide in order to react. So the two conditions have to be met. They must collide with sufficient energy, and they must collide with correct orientation. And what exactly does that mean? Well, here I have two molecules. Maybe it's hydrogen, H2, and iodine, I2. Well, what the heck? So if this is my hydrogen, this isn't working. If this is my hydrogen, there it goes, now it's working. It's moving around, and so is the iodine. So if hydrogen's approaching iodine really, really, really slow, and it kind of glances, is that going to be enough energy to break the bond? The answer is no. So if it comes zooming in, zooming in, like that, all right, can it have enough energy to break the bond? The answer is probably. All right. So again, it has to have the correct energy. Now, what's this about orientation? If this is going to collide like this, is it necessarily going to break bonds and form new ones? The answer is probably not. But if it comes in more like this, can it then break bonds and form new ones? The answer is yes. So if these molecules were to collide, they may for a brief moment stay together now. And this would be like an activated complex where all the bonds are together. And eventually, this is at such a high energy that the new bonds are going to form. So eventually that these new bonds are going to form, and I can do something like this. And why would this kind of a bond arrangement occur? Because it's more stable. It's going to be at a lower energy. So if I were to show an energy diagram of something like this, it would go along these lines. So find a blank spot and kind of start jotting this down. So here I start with my axes. Energy is my y-axis, and reaction progress, or sometimes otherwise known as reaction coordinate, is my x-axis. And I'm starting here with my hydrogen iodide and my hydrogen gas H2 and my iodide gas I2, or vapor, or whatever we call it. So, and then what happens? They're colliding. And so when they collide, what's going to happen to their overall energy? Their energy, because they're going to have, a net sum of energy, their energy is going to start increasing. So this grouping here is going to start going to a higher energy level. So that's the amount of energy that is required for these bonds to break. And then at the very top, this is called an activated complex. This arrangement of atoms is at the highest potential energy. And what's going to happen next? These bonds are going to break and then form new bonds. So now we have these hydrogen iodides that are much more stable. And so because they're more stable, they're going to have lower energy. And they're going to be down here. So now these are free to move around. So I can continue my graph. And that's how much I end up. Now before, we've always called this the delta H of the reaction. So this reaction is actually exothermic because the energy is lower with the products than it was with my initial reactants. But what is this hump? Well, this area right here is called the activation energy. And that's the energy that's required to break those bonds. So once you've reached that threshold where you have enough energy to break all the bonds and you form that activated complex, that's when all those four atoms are kind of all sort of bonded but sort of not at the very top of that hump. and the bonds were kind of broken, but there was still attraction going on there. And so then what happened? And they hooked up, like magnets snapping, and energy is released, and now they're at the lowest energy level. So let's kind of see what's going on in your notes here. Let me go back to this page. And here we go. So they must, here we go, they must collide with sufficient energy. I try to show you that. And they must collide with the correct orientation. And so here's what's going on here. So we're actually using hydrogen gas and oxygen gas in this example. Notice that the energy of the reactants is kind of in the middle someplace. And then they are colliding, hopefully with good orientations. And at the top of that blue arrow, it says activation energy. That's where you're going to make this activated complex, this arrangement of probably those 6 atoms sort of together, sort of not. And then they snap together to make water, and the energy is much lower. So also look over on the right hand side over here. Notice that because of the orientation, that there's no reaction at these couple spots. But where the orientation is correct, there is enough energy to collide, and the orientation is correct, is going to actually says lead you to the product. So it says the energy required for atoms or molecules into the activated complex. That's that transition state I was trying to describe to you. And it's the minimum energy required for an effective collision. Now, let's kind of go back and think about what things we can do in order to have these collide with sufficient energy. I know, for example, like I like my sweet tea, and I like to put sugar in my tea. And if I have cold water and sugar, it doesn't dissolve very well. So what can I do to make that dissolve more? I can heat it up, all right? So do you think there is any kind of relationship between temperature and this energy? And the answer is, well, yes. Think back with all those examples we've done in this whole chapter. Hasn't those K values always been determined by what temperature it's at? So at 25 degrees C, K equals. At 600 degrees C, K equals. Well, temperature does play a very important part. What is something else that we could do to provide energy so they collide, with enough energy? Well, you can stir it, for heaven's sakes. I mean, I stir my iced tea so the water will dissolve the sugar better. Even things like surface area can help, because the greater the surface area, the easier it is for dissolve and reacting and whatnot. So I think we saw that way back when we talked about the dissolving process. So all these things can go in effect as to how can you get these molecules to collide. Well, you have to have enough energy, and you have to have the correct orientation. We talked earlier, what if you flooded this? What if you double the concentration? Well, if you have more concentrations, you're going to have more collisions. You're going to have a greater probability of having this effective collision. And an effective collision is with sufficient energy and correct orientation. So let's scroll down here. Some important dude, the Arrhenius equation. We're going to find out who Arrhenius is a little bit later on too. We talk about acids and bases. He came up with this equation that relates constants and collision frequency and the steric factor. What is a steric factor, for heaven's sakes? A steric factor is the orientation. So it's representing the fraction of collisions with correct orientation. So they looked at all the different possible arrangements they can collide and be not correct, and then how many would be correct. So then he says, well, this is a complicated equation. Let's kind of work on this a little bit. And so he combined the Z and P to make a capital A, and that's the frequency factor. And so then if once again, we're talking about exponents. We're talking about E, like we did before with a natural log. So if we were to manipulate this equation, so I took the natural log of both sides, and then, as you know, if you remember your law of logs, that if you're multiplying things within the natural log, you split them up and you add them. And this capital A is equal to the activation energy. That's what the EA is, your activation energy. That is that hump on that graph that we're talking about, divided by RT. Remember what your R has to equal. It has to equal that 8.3145 joules per mole Kelvin, because this is all talking about energy. And T, of course, is temperature in Kelvin. And if we separate it out, look what happens. If we could graph this, y is the natural log of the constant, Your slope is your activation energy over R, but it's the negative because slope's going to be a negative number. 1 over t is going to be your x, and then the natural log of a is going to be your y-intercept. So again, graphing is such an important tool in chemistry. So keep this equation in mind. So kind of get to know that natural log of k equals negative activation energy over r times 1 over t times, or excuse me, plus natural log of a. Well, we have some problems that goes along with this. So it says determine the activation energy for this particular reaction. Well, here is, look at the graph. What's your y-axis? It's the natural log of k. What is your x-axis? It is the 1 over temperature. All right, sorry, I had to sneeze there. So they're asking what is the activation energy? Well, this graph is setting you up to use that Arrhenius equation on the prior page. So why don't you work on it, pause this recording, and then the answer will just magically appear. So pause it right now, give yourself a few seconds, and then you can turn on again when you're done. Ta-da! Here's the answer. So I just rewrote this Arrhenius equation where natural log of k, which is your rate constant, equals the negative activation energy over R. R is the rate law constant, or the gas law constant, which is 8.3145, times 1 over temperature plus natural log of A. Now be careful. This A is not like a concentration of the initial amount like we've used A in the past. This is that frequency factor A, which is the frequency of the effective collision. So it's a different A. Don't think that is any kind of concentration. So they're asking for what is the activation energy. So that's right here. That is your slope. So your slope they gave you is negative 1.2 times 10 to the 4th Kelvin. So negative EA, activation energy over R, is equal to negative 1.2 times 10 to the 4th Kelvin. Here you just see me solving for the activation energy. Now look at your units. Pretty clever how this works, because what's going to happen here, your kelvins are going to cancel out, leaving you with joules per mole. You could also make this into kilojoules if you want. It would be 100 kilojoules per mole divided by 1,000. So isn't that the same kind of units that you would see typically for an energy? Well, yes, it is. All right, problem number 22. Notice what's happening here. The gas phase reaction between methane and diatomic sulfur is given by this equation. They're giving us a temperature value. This is the first time that temperature is part of your equation. So at 550 degrees Celsius, the rate equation, the rate constant is 1.1 liter per mole times seconds. And let's change the temperature. There's a new temperature. And the rate constant is 6.4 liters per mole times second. Using those values, calculate EA for this reaction. Now, in order to do this, I'm going to probably use another whole board because this is a long problem. And how I approach this is that, what term did they not give me? I know nothing about this A, this frequency factor. So in my math, I solved for A and made that equal to the two conditions where the temperature of this first one is 550 and the temperature of the second one is 625. So using that, why don't, again, you pause this, you work on it. It's probably going to take you several minutes, all right? At least I would guess 5 minutes. And then come back and turn this back on, and the answers will again magically appear. All right, so here's the equation. There's the Arrhenius equation at the top right up here. So if ln of k equals negative activation energy over R times over T plus natural log of this frequency factor, I solved for the frequency factor. So I added EA to both sides. So now we have natural log of A equals natural log of K plus EA over R times over T. So if this is equal to A, so the first condition is equal to natural log of A, so does the second condition equal to natural log of A. So now I just set these sides equal. So natural log, here's condition number 1 of 1.1 plus EA over the R value, and I put in the unit here, but I'm starting to run out of room, joules over mole K, times 1 over 823 Kelvin. And note what happens then, excuse me, with the kelvins. They cancel out. And so they will cancel out here if I wrote my units in. So equals natural log of 6.4 plus EA over 8.3145 times 1 over 898. That's the second temperature. So now I actually started putting numbers in. So natural log of 1.1 is this number. And oops, I'm going to run out of time. see my work, pause it if you need it. And there's the rest of my work. I'll catch you later. Bye.